this session will be recorded. And so I will start to welcome everybody to this third webinar of the series of webinar for the CFTC internship program. So today we'll have Professor Rui Santos. So Rui is a professor at ISEL and an invited professor at FCUL. He won in 2018 the Scientific Award of the Instituto Politecnico de Lisboa and has an impressive list of more than 600 collaborators worldwide. So Rui will talk to us about dark matter and the challenge of the field. So in the past, I've seen some amazing presentations from Rui, but live. Now he has the task to do the same in front of a computer. Let's see if it works. Thank you, Rui, for accepting to talk, and the internet is yours.
Okay, thank you, Cristóbal, for the nice presentation. So I'm going to tell you today how to find dark matter, although we don't know if dark matter exists. But if it exists in the form that I will tell you, then this is the way to find it. So let me start, or not. Okay. So let me start by telling what I will be talking about. So first of all, we have maybe too many hints of dark matter, and this basically means that we have hints of something that is happening that we don't understand. But the best way to explain all of them with just one thing is to think of it as something that we call dark matter, and that dark matter is a particle. Okay, but still we don't know if this particle exists. And then the point is that if it exists, how can we search for it at accelerators, and in particular at a Large Hadron Collider? And then I will tell you if and how we can see it elsewhere. And then some conclusions, although they are not conclusions because we saw nothing yet. Okay, so probably you have all seen this. So this is the first time that people discuss about, well, Fritz Zwicky, not people, discuss about dark matter the way we see it today. He was discussing the discrepancy between the observed and the expected rotation velocity of galaxies. And so he wrote in a paper, should this turn out to be true, the surprising result would follow that dark matter is present in a much higher density than radiating matter. So this is something very simple to understand. You just, it's something from basic physics that you do in the first year or even before that. If you have, for instance, a satellite that is revolving around the Earth, you see here one in this picture. So this is the satellite, and if you put it at a distance of 640 kilometers from the center of the Earth, you know exactly what is the velocity of the satellite. So this is something extremely simple. You just have this equation that you have seen hundreds of times, and then you do now the same. It's a bit more complicated, but the idea behind it is the same. You do the same for the rotation curves of spiral galaxies, and then you see that you have two curves here. So this is what is called the Keplerian prediction, because you're moving away from the matter that you see that has some kind of light that you can see, and this in red you see the experimental results. So it's very clear that if the galaxy had only this visible matter, then the expected behavior for radius above 10 kiloparsec, this is the typical radius of a spiral galaxy, that the velocity should behave like you have here, which is the same as for the satellite. I mean, when you move away from this radius from 10 on. But what you see is that this is the distribution curve for the luminosity, but not distribution curve for the mass. And so you see that the distribution of light, what we can see, does not match the distribution of mass. And this is something very old. So this was the first strange thing that happened that maybe could be explained in some other way. But the point here is that when you start putting a lot of the experimental evidence, which basically comes from gravitational problems or cosmological issues, and when you put all this together, dark matter is the best way to solve all of them at the same time. Okay, but it is not an answer because physics is still an experimental science, and so we need to see dark matter before we say that there is dark matter. So I will not go in detail through all the possible, the experimental strange things that are happening from the rotation curves to gravitational lensing. But when you put this together, as I said, then the best way to explain everything at the same time is to think of dark matter as a particle. Now, when you start thinking of dark matter as a particle, then you want to understand how it interacts with the other standard model particles. So you see here something that's called the bullet cluster. You have two galaxies colliding, and you have lots of different observational data superimposed, and so you have from optical and X-ray, you have this hot and dense gas, and this is the typical shape of a high-speed collision. But if you look at the lines of the gravitational potential that are obtained from gravitational lensing, then you see that dark matter is concentrated around the galaxies and is not affected at all by the collisions. So if dark matter is a particle, then it interacts very weakly, dark matter between dark matter with dark matter and dark matter with the standard model particles. Okay, so this is another point, another important point. Now, if we go to cosmology, you know that in the standard model of cosmology, and this is today is something that every physics student knows, that it is, we assume that just after the Big Bang, the universe was really hot and then inflated and then cooled down. And these effects of this very fast cooling down predicted a very low temperature radiation that we could still see today. And so this radiation was finally seen in 1965 by Penzias and Wilson, and they found by accident, or so they say, that there is a radiation of 2.725 Kelvin, and this gave them the Nobel Prize of 1978. Now, what is the relation with dark matter? What can we learn from this? Now, there were three experiments, one called COBE, the other one WMAP, and the last one Planck. And they were looking for fluctuations in the cosmic background radiation. And because you're looking for fluctuations, this is related to the matter density fluctuations in the early universe. So if you take the results from Planck and you put it together with the standard cosmological model, then you can use these fluctuations to say something about the different types of matter that existed, or at least the density of matter. If you impose that the matter is there, like dark matter, then you can say how much dark matter you had at that time and what happened to dark matter after that. So if you assume that there was a time when all particles were in thermal equilibrium, then the universe expanded and there was a freeze-out. So all the unstable particles disappeared. This means decayed. So for instance, you know that you have the electron and then you have the muon, and then you have the tau. And the only difference between these three particles is that they have different masses. So, of course, the tau can decay to muons and electrons, and the muon can decay to electrons. So if the energy is really, there's not much energy available, in the end you'll have only electrons in the universe. So all these unstable particles disappeared, and of course the number of stable particles reached a constant. And this constant is called the thermal relic density, which we expect as still the same value today. So you can think of it, if you look at the density of dark matter, you can think that so there was a time when there was still although you have very small cross sections, you had so many particles that the particles kept colliding and giving rise to other particles. So that there was a lot of stuff going on. But at some point, if the distance between these dark matter particles become really large, then if you have a small density and a small cross section, then particles cannot annihilate. And at that time, and because they are stable, the density of the particle from a certain time on, this density of particles remains constant. So this is also a mechanism called freeze-out. Of course, there could be other mechanisms, but if we believe that there were a lot of dark matter particles in the beginning, and then the density universe expanded, the density decreased, and because the density decreased, if you put together with the cross section, then this means that that the stable particles are just there, and so they are still there today. Now, of course, I don't have to explain in more detail why is it so interesting, because we can see it. Of course, it changed our perception of the universe, not only dark matter, but also dark energy, because you don't remember, but older people that are listening to the talk, they were told that everything was made of quarks, and everything that we saw in the universe were basically made of the standard model particles. And so today it seems that there are more dark matter than standard model particles. So this is really very strange. It is also interesting because it's, I think for a long time, disciplines were really apart, and this is probably the most interdisciplinary subject inside physics, because it uses relativity in nuclear physics and particle physics and cosmology and a lot of classical physics in between as well. And then, of course, the mystery, which is something that we like. We know, or maybe we don't, that it exists. We know where it is, and we have a lot of hints on how it behaves, but then we have no idea what this particle, if it is a particle, is. Okay, so now to do something with dark matter, we first have to agree on a region of mass, because we have to look for it. So the first question is if dark matter is a WIMP. So a WIMP is a weakly interactive massive particle. So it is something that we believe could be between, say, 1 GeV and 1 TeV. And just to give you an idea, the proton mass is 1 GeV, so it can be like 1,000 times mass with that is 1,000 times larger than the proton mass. So we know, or it seems that it is massive because it is cold. I mean, it is not relativistic. The neutrino cannot be a dark matter particle. It has to be stable. It has to be neutral. It has to have weak or none interactions with itself and with the standard model. So now, this is the beginning of the search. We know, or at least this is what we'll search for. Maybe we're searching in the wrong place, but this is what we'll search for. And you have here in this cartoon you have the different possibilities. So if you read it like this is called indirect detection. So this means that you have two dark matter particles colliding, and then you have two standard model particles appearing, or two or more. So this means that if you see either a photon or an electron-positron pair coming out of nowhere, this could be a sign of dark matter. So if you see it in this direction, then this is direct detection. This is a dark matter particle that collides with a standard model particle and then gives a dark matter particle and a standard model particle. So this is what we would really like to have is direct detection. And then if you see it in that direction, then this is collider production. So like, for instance, at the Large Hadron Collider, you have protons colliding. So this means two standard model particles colliding, and then you have dark matter particles that are being produced, okay? So now this is what we have to do. We will be doing searches for dark matter, and we don't see dark matter, so this is really a problem, and so you have to be a certain type of person to look at into this problem. Okay, so let me tell you then how we do this. First of all, we build a model. So this we already know. This is the standard model. The standard model is working. Is working fine. You have the quarks, you have the leptons, and then you have the strong force. You have here the gluon, the photon, and the carriers of the Weak's force, W and Z, and then you have the Higgs. So far we found only one. And so to build a model that includes dark matter is something very simple. You just take the standard model and you assume that there is some hidden sector, and you have some function, some potential that connects the things that we see with the things that we don't see, okay? Sorry again. And so you have this term in the Lagrangian. The Lagrangian is what describes everything. And then you just know that the dark matter particle that you're building has to be stable. But of course, it has to have some interaction with the standard model, because otherwise we'll not see it, and then there's nothing to be done. Okay, so to make sure that the dark matter particle is stable, then you can do it by using, for instance, a new quantum number. So why is that so? So if you look at the QED Lagrangian, which is written here in the wrong form, but what is important here is that you have an electron, a positron, and a photon, and this means that every time you have an electron colliding with a positron, you don't know what the outcome is, but you are 100% sure so far that charge is conserved. So this means that you can have a number of neutral particles, say gammas, z's, h, but if you have a quark being produced, you also have an antiquark. So this is related to gauge symmetries, and this means that these gauge symmetries give you the rule for interaction, and they mean that there are conserved quantities, in this case the electric charge. So now we use the same idea, and we define a new quantum number. Let us call it darkness, just because it's nice. And now suppose that we have a vertex like the one that you have here, meaning that you have, for instance, a Higgs that could decay into two dark matter particles. Is this possible? And the answer is yes, because the model should conserve darkness. So if I say that the Higgs has darkness 1 and the dark matter particle has darkness -1, then you have 1 on one side, and -1 times -1 is 1 on the other side, and so this is all fine. Okay, so what you have to do is to make sure that the particle is stable, because otherwise, if you look at the second graph that I have here, suppose that you have a dark matter particle that would decay into two other particles. Okay, so this is not possible because darkness is not conserved then, because the dark matter has darkness equal to -1, so it's -1 on one side and 1 on the other side. And of course, if this was possible, then this means that the dark matter particle could decay and then it would not be stable. So that's the reason for using this quantum number, to make sure that you get a stable particle in the end. Now, after you build a Lagrangian like this, whatever the Lagrangian is, then you know that you can produce dark matter at a collider. And here you see the production of dark matter. You have exactly something that could happen at the LHC. You have a quark colliding with an anti-quark, and then you have a gluon coming out and two dark matter particles. So this is a process that, from the point of view of charge, is possible. From the point of view of dark matter, is also possible. And so this is something that we expect to see at the LHC. Now, after we finish building the model, then a collider is very handy. So let me just tell you what are the important things in a collider. So first, you have here on the left, you have the beam pipe. So you have the protons going around inside this beam pipe until they collide. Then you have a lot of people. People are also important because they take care of stuff, so that we can then see the things that we see. And then you have here the Atlas and CMS. These are the places where you are going to see what is happening. So these are detectors, and the detectors have a lot of different layers, so that they can detect photons and they can detect charged particles, and a lot of different things, just for you to know that these are the places where the particles are detected after the collision. Okay. Now this is an impression of a collision. So you see here you don't see the particles, but you see either the traces of charged particles, or you see the energy that is deposited on the detectors, okay, on the different layers of the detectors. Okay, so then, sorry. Okay, so why do we do this? So the idea is to look at the past, and I usually show this slide because it's easy to understand if you are a biologist. So suppose you decided to collide a lot of strange DNA, and then you can produce, let's say, on one hand a penguin ancestor, and on the other hand a dinosaur. And just the difference, because I take one of them to be like the tau or the muon. If you take the penguin ancestor, it would decay then to a regular penguin that you can see today. So this would be a tau or a muon decaying into an electron. Or you can just produce particles like the Higgs that then disappear. So if you want to see them again, you have to create enough energy so that you can look at the past for a brief moment. And this is what you're doing. So this is where you will live. Here we are. And then as you move along back in time, so this is you moving back in time and with increasing temperature. And you see here the accelerators. These are older accelerators like Greek and the Tevatron, and you see here the LHC. So you see here that this is really the place where you can produce muons and quarks and taus and z's and w's, because you are in this region here. And so you are going back to the beginning, closer and closer to inflation and to the Big Bang. Okay, so now we have a collider.
We are almost in the end of the 20 minutes, just to let you know.
Okay, okay. So now let's see how we look at at dark matter production. So if you just collide two particles and you produce dark matter particles, you will see nothing, right? Because it is invisible, so you get two invisible particles. But there's one thing that you know that there is conservation of energy, and so you know something about the missing energy. Still, if this is just what you see, you can also see it here. So if you just see the proton beam and two undetected particles, then there's nothing for sure that you can say about it. So the idea at the LHC is to look for what is called mono-Z or mono-jet or mono-Higgs events. And this means that you will be producing dark matter alongside with either a jet or a Z boson or a W boson or a Higgs. And then, of course, the rest will be missing energy, and you know how much this missing energy is. Okay? Oh, sorry. Okay? And of course, you know this missing energy. You see it here in the transverse plane. I can explain this later if you want. But you see here the jet and the missing energy. Of course, this missing energy can also come from other sources. And one obvious source is neutrinos, because you also don't see the neutrinos. So what people do then, both in CMS and Atlas, is that they put all this together. They put together all that they know is invisible, and they have some clear energy distribution for all the invisible stuff. And then on top of that, they see what the dark matter from a particular model will increase this invisible part of the energy. And if you see some difference there, then this means that there is something that you cannot explain, and then you start looking for it in more detail. So far, nothing was seen. So another possibility is to look at a production, for instance, of a Higgs, and then the Higgs decays to dark matter particles. So these are called the invisible decays of the Higgs. Suppose that you have a collision, you produce a Higgs and together with other particles. And then you just see the other particles. So this means that the Higgs disappeared into something that you cannot see. And this is something that you can also look for. And so far, if you assume, of course, you have to assume something. If you assume a standard model production of the Higgs, then you know that the fraction of the Higgs that can go to invisible things is below 24%. Okay, so this also gives you an idea of constraints that you can input, that you can put on dark matter particles if they are below the mass of the Higgs over 2. Okay, so this is basically what you can do at the LHC, and together you can put all this together, and then you go for specific models. This is a type of model that we have worked with, the inert 2HDM, and for this model, then you do exactly what I described, because this description is completely model independent. You just need to have the production of some particle that you can see from the standard model, and together with this particle, you have a lot of missing energy. And this missing energy is something that will give you a hint of something that can be a dark matter particle. But remember, it's just a hint. Okay, so let me just show you a few slides about indirect detection. So this is collider searches, and collider searches means missing energy searches, and this means that you can have a hint for dark matter, and that's all. Another hint that you can have comes from indirect detection. So in places where you have a lot of dark matter, you could have collisions of dark matter giving rise to, for instance, photons, and this is done in many experiments. One of them is the Fermi Large Area Telescope that detects gamma radiation between 0.3 and 300 GeV. And of course, with this, you can see if there is dark matter that can be annihilating and giving rise to photons that you did not expect. But of course, even if you have a lot of hints, you need to direct detect dark matter. And this is done in many experiments. One of them is with a bunch of xenon. And in this case, you have the dark matter. If the dark matter hits a xenon atom, then the atom recoils and excites others, and this causes a light flash, which is this S1 here. And then this collision also frees electrons, and this means that they will travel. And they will excite to make another. They will excite the gas to make another light flash. And so, if you see something like this, this is probably a dark matter particle, and this will give you then direct evidence of dark matter for a given mass. And okay, so this is the same thing, and these are the different experiments, and the experiments give you can give you limits on the cross section of interaction with dark matter with standard model particles as a function of the dark matter mass. Now, these are, then you can put this together. This is the last slide I will show you. You can just put this together. The searches at the LHC and the searches of direct and indirect, and you can put and have the bounds on dark matter nucleon cross section as a function of the dark matter mass. And so these are basically what we have today. Although this piece here for the standard model this is not really for the standard model. These are some cross sections that you assume that are really simple, and then you get these limits. Of course, these limits could be evaded if you have a more sophisticated model, but this gives us at least an idea or where we stand on the possibility of finding dark matter in the future. Okay, and this is more or less the same, and so these are the conclusions. So we have this all these gravitational and cosmological effects that I will only say that are better explained with a particle, with a dark matter particle, and it seems to be cold and with very weak interactions with the standard model particles. So far, we have no candidates, and of course, as usual, the theory has too many candidates. Now, again, just to tell you again what I just did, what I just told you. The accelerators, both the LHC and future ones, cannot confirm the existence of dark matter because you will always need direct detection to say that there was something there. Of course, then even for the LHC, even if you see some hint, of course, this could be signal of just a long-lived particle. And we could have a lot of dark matter candidates at the same time. Okay, and I think this is enough.
Okay, so thank you, Rui, for your talk. It went a little bit above the time limit, but so before we finish and wait for some questions or not, I would like to ask you something that is, because since we are doing this is an internship for physics students, and a lot of them are interested in the particle physics area field. I would like you, if you could explain what is the path that a theoretical particle physicist should do, or a student should do to be a theoretical particle physicist like you, and what will be the difference if you want to go experimentalist or more in a theory?
I don't know if I understand what where you want to go with your question. I mean, if you want, if you mean what you should do from the point of view of your life, or what exactly is the question?
Or your studies or the career, what he or she should choose to be a particle physicist like you?
You mean from a point of view of studies? Because there are so many answers for what you are asking me. I mean, well, first of all, of course, you do a master in particle physics, and I think this is the right place to understand if you like theory or experiment better. Okay, because or even before that, if you have some projects, it's even better if you have some projects before that, because it is very clear. You see people that start with theory in the master, and then they move to experiment, and people that start with the experiment and move to theory. So I think the master is the right place to understand what you like best.
So it's quite easy to change from theory to experimental in particular.
At the master level, I would say yes. For instance, Duarte did the master first in experiments, and then he moved to theory and is doing very well. So, and this was also happened in the past. So I think that's not really a problem. I mean, if you look at what we're doing, Rodrigo is doing partly a theory, partly experiments. He'll probably do this until the end. So this means that you'll be able to do a lot of different stuff. I mean, it's not clear if this is the right path or not, because it really depends on what will be happening 4 years from now, you know. So I would not say, look, now it is really better if you choose theory, or it is really better that you choose experiment. It's not clear at all. And even in particle physics, I mean, we know that we have this collider for many more years. But if you're just starting, you have to start understanding what is happening in the interface with cosmology, with astrophysics. This is really important at this moment.
Okay,
so
thank you for your answer. So, since we have no question in the Q&A, I think we can thank Rui again for his nice talk, and we'll see all of you next Monday for our next webinar. Thank you, Rui.
Okay, thank you. Bye.
Bye.